has yttrium, terbium, actinium, rubidium, boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium.
For this dot point, you need to know a bit more again about Le Chatelier's principle. So before I start, I quickly want to cover Le Chatelier's principle, the basics of it. And I'll recommend you watch this video if Le Chatelier's principle isn't really that familiar with you, or if you want to brush up on Le Chatelier's principle in more detail. I recommend you follow the link and watch this video. But Le Chatelier's principle is really important when it comes to the Haber process, and you need to know it for this dot point as well. So the actual Le Chatelier's principle is basically a reversible reaction which reaches a state of equilibrium where concentrations of reactants and products don't change unless the system is disturbed. So what that means is it's a reversible reaction, right? So Le Chatelier's principle says if we have a reversible reaction, which will be indicated by this arrow here, what that means is that the reactants and the products have reached, at some stage they will reach a point where both concentrations won't change anymore. So for example, if we have 4 reactants number 1, 4 reactants number 2, and 2 of these products, if that's what we have, and this is at equilibrium, so if this is at equilibrium, then this won't change, right? Some of them, so for example, this might break into 2 again, right? This product here might break into reactant 1, reactant 2, but as soon as that happens, 2 more, so other 2 ones, so for example this one and this one, these ones will combine to form a new product. So more or less, even though there is movement, things break apart and build up again, but overall the concentrations will stay the same, right? So if something breaks up, something new will be built up again. And yeah, at equilibrium, everything will stay the same. But what Le Chatelier's principle says is there are ways we can disturb this. So there are ways we can basically get this standoff and interrupt it. And the 3 ways that we can do it is by changing the temperature, changing the pressure, or changing the concentrations of products or reactants. And when it comes to the Haber process, we actually use all 3 of these. We manipulate all 3 of these to get maximum yield. But in this video, we have to talk about temperature specifically, because dot point itself says explain why the yield of the product in the Haber process is reduced at higher temperatures using Le Chatelier's principle. So I have to explain why the yield of the product is reduced when it comes to the theory of Le Chatelier's principle and decreasing the temperature. So I'll go over what that means. So here we have the reaction which happens inside, or that we do with the Haber process, right? So this is the Haber process. Here we have our nitrogen and we have our hydrogen gas, and this will react to form our ammonia. So this here is the ammonia. Because this is a reversible reaction, what it means is some of these can break off again and build into the reactants, and some reactants can join and make some of the product, right? So the reactants are here, and the products are over here. Now it's also important to realize that the actual whole reaction is exothermic. So if the forward reaction happens, if the reactants come together to form the product, what that means is there's a release of energy. So whenever this happens, whenever our nitrogen and our hydrogen come together to form ammonia, whenever that happens, we have energy being released. And energy being released basically means that this will increase the temperature. Energy increase leads to increase in temperature. Right, so the more ammonia that is formed, the more our temperature increases. Now the interesting part is with the Haber process is we have a temperature of 500 degrees Celsius. Right? So 500 degrees Celsius, what does that mean when it comes to the actual yield? Remember what this is reduce? It says explain why the yield is different. Yield means sort of the percentage of ammonia that we get. And does it go almost to completion? Does almost all of these combine to form ammonia? That would be 100%. Or is it some of them staying as reactants and only a few forming to ammonia, that would be less than 100%. So 100% would mean that this goes to completion. Basically, all of these react to form the product. Whereas less than 100% means, if for example it's 50%, that means 50% are still this and 50% are ammonia. Right? So that's what's meant by the yield. How many percent of them kind of usually go. Now, when it comes to 500 degrees Celsius, what would that mean for the percentage yield of ammonia? Well, 500%, what that would mean, 500 degrees Celsius, what that would mean is we would actually shift to the right. Sorry, to the left. So we go this way, which means our actual product will sort of break down and form the reactants again. Will form nitrogen and will form hydrogen gas again. So why would that be the case? Well, if we have an increase in temperature, remember the actual system always tries to find equilibrium again. It tries to, whatever disturbance there is, it tries to break it apart again. It tries to reverse it. So if we increase the temperature, if we've added 500 degrees to the system, what's going to try to do is it is going to try to get rid of those 500 degrees Celsius. And how could it do that? Well, if it goes in the other reaction, in the other direction, what that means, instead of actually releasing energy, which would happen if it goes in the right direction, if it goes the left direction, what will happen, it won't actually release, but it will absorb, right? So the left reaction means it will absorb heat. So we've added 500 degrees Celsius. The system wants to remove those 500 degrees Celsius, and the best way it can do that is by going to the left, forming more reactants, because that will absorb heat. It will be the opposite of the forward reaction, which means we'll try to basically combat the 500 degrees Celsius that way. Now, that's obviously not ideal when it comes to the Haber process, because we want to be actually getting ammonia. That's the whole purpose of the Haber process, to make ammonia. So why do we do that, and how do we still get more ammonia by having a high temperature? Well, what you can imagine is that whole idea of rate of reaction, which we talked about in the last video, rate of reaction. And if you haven't seen the last video, make sure to watch the last video because they connect quite well. But the rate of reaction is how fast a reaction occurs, so the speed of it. So how many reactions there are per second. So how many reactions per second? Now, if we're, for example, at room temperature, even though whenever there is, if we are, let's say we're at room temperature and we have high pressure, maybe somewhere in the 1,000 atmospheric pressure, that would be close to 100% yield, right? That would be a very high yield if we have this scenario. This would be very high yield. It's very high yield. But the problem would be, because the temperature is so low, they're going to be moving at such a slow pace, and when they do collide, basically the energy isn't strong enough. They're not strong enough to actually form the product. So even though, if the reaction does go ahead, ammonia will be produced and it won't break down again into its reactants. The problem is the rate of reaction, because the low temperature is so slow that, for example, let's say this only produces one reaction per second, right? So one reaction per second. The good thing about this reaction, it will stay ammonia, or the likelihood of it staying ammonia will be quite high. But the problem is it's only one reaction per second, because the temperature here in this scenario was only 25 degrees Celsius. Whereas in the other scenario, let's say we have it at 500 degrees Celsius. What that would mean is they're actually going to go a lot faster. Right? They're going to go faster. They're going to have more energy. And when they do collide, that's going to be a higher chance for them forming ammonia. So for the reaction to go ahead, right? So when they do collide, the chance of the reaction going ahead is a lot higher because they have more force that they can apply, which means you can, for example, just sort of see it as 10 reactions per second. So the rate of reaction is a lot faster, 10 reactions per second. But yeah, the problem might be that, let's say only 50% of those will actually stay ammonia. The other 50% will break down back into nitrogen and hydrogen gas. But overall, that would still mean we would have 5 moles of ammonia. Because if we have 10, and 50% break, that means we still have 5 left. Whereas in the other example, even though they all stayed, we only have 1 reaction, which means we only have 1 mole. So 1 mole versus 5 moles. So you get the idea, hopefully. And how it's also with the activation energy in terms of why we have high temperatures. So if you are a bit confused about the activation energy, make sure to watch the last video. But yeah, the idea is we have the Chatellier's principle tells us that if we have 500 degrees Celsius, we're going to face one problem, which means that we're going to have a lower percentage yield of ammonia because the whole procedure, the reaction is going to go to left, which means there's going to be more reactants being formed than products. But the reason why we have as high temperatures is because it speeds up the rate of reaction, which means that even though we have a lower percentage yield, we're going to have more reactions happening, which means overall we're going to have more ammonia. But yeah, hopefully that was useful. But that's basically the point. But I hope that was useful.
Thank you for watching.